It's my great pleasure to introduce you Marco and Luca. So Marco Di Felice is a full professor at the University of Bologna, where he founded the IoT Prism Lab. He's also a faculty member of the International PhD program in Engineering and Information Technology, Infrastructure and Environmental Monitoring and Risk Management. And he also served as an associate editor for IEEE Internet of Things Journal and Ad Hoc Networks Journal. And he authored more than 160 scientific articles on wireless, pervasive, and mobile system, interoperability, and IoT data processing and platforms. And together with him, there's also Luca Sciullo, is a junior assistant professor who authored more than 30 papers in international conferences and journals. He was a visiting researcher at Huawei, a European Research Center of Munich in Germany. And of course, his research interests include wireless system, Internet of Things, Web of Things, digital twin, Industry 4.0, and blockchains. So, guys, the floor is yours. Please go ahead.
So again, thanks a lot for the invitation. It's a pleasure for us, and also I think is a great opportunity. In this presentation, we are going to showcase the research activity in our lab at Unibo. Of course, focusing on aspects of IoT, interoperability, and Web of Things. As Cristiano was saying before, I'm a full professor in computer science, and in my department, I'm directing a research lab called IoT Prism. In the IoT Prism, we do more or less research on the vertical of autonomous IoT systems, where autonomous means, for instance, capabilities of integrating data from heterogeneous data sources, heterogeneous devices, means possibility of offloading task over the edge cloud continuum, or possibility of running intelligent tasks, mainly machine learning tasks, in distributed federated environment, or inside constrained IoT devices. So all these icons here have been created by using generative AI. However, in the IoT Prism Lab, we have biological brains. So this is our group, and of course we are always open. We're always looking for collaborations and project participations. So regarding the Web of Things initiatives, I have to say that we more or less we follow the initiatives of the working group since the beginning, and we try to contribute in an unofficial way, but in an official way, but with different contributions. For instance, investigating and developing connectors between the Web of Things and other interoperability standards like RWED, FireWare, trying to extend the plethora of supported devices, for instance, bringing the Web of Things to constrained IoT devices like microcontrollers, or generally speaking, developing new tools for the Web of Things ecosystem. And this is more or less the focus of our presentation today, because today we are as you could see from the title, our presentation will mainly focus on digital twin. And in this slide, I'm trying to summarize the main concept behind the digital twin approach. So without loss of generality, we assume to have a real system, a physical asset, a physical IoT asset. We will provide some example later. And we collect data from the physical assets by using heterogeneous data sources. Can be ground sensors, can be mobile sensors, can be rovers or drones. We collect IoT data from the environment, and we integrate the IoT data with external knowledge. External knowledge can be simulators, can be machine learning models. in order to create the digital twin, so a virtual reproduction of the physical asset. And the virtual reproduction can be used in order to run what if analysis, in order to understand the correlation between input and output parameters of the physical asset, or to do prediction of the system state at time t plus k, where k can be 1 month, 1 day, 1 week, and so on. So basically, in our presentation today, we are going to show how we leverage the Web of Things standard in both the stages of the digital twin generation. So in the first part, for the real-time monitoring of the physical asset, and in the second part, for the semi-automatic spawning of the digital twin of the real system. So the first part covered by me will be more the first part will be more related to applied science, while the second part will be more scientific research. Indeed, in the last years in our lab, we have been involved in different projects focusing on different use cases of the IoT, from smart agriculture, healthcare, smart building. And since we don't have so much time today, we are going to focus only on the last use case, so on smart buildings, and in particular on application, how we applied Web of Things technologies in the context of structural health monitoring. So in few words, structural monitoring is an interdisciplinary area which try to assess the structural solidity of civil buildings and critical infrastructure, like for instance bridges, by combining sensing, data analytics techniques, and of course domain knowledge coming from the civil engineer perspective. In Italy, there's lots of interest, not just in Italy, but especially in Italy, there's lots of interest on the application of a SHM solution. First of all, because of the presence of critical infrastructures, and also because of the cultural heritage. Because of cultural heritage building. I guess if you had the opportunity to visit Italy, or maybe if you are planning a journey to Italy, maybe you are planning to stop in Pisa to visit the famous Leaning Tower. Actually, I don't want to reduce your expectation, but it seems, I don't know, it's possible that the situation is improving. So the tower is tilting less than before, while in less famous, but probably more critical, in Bologna, in our city, there is another medieval tower, and here there is an high risk for collapsing event. So in the last years, we have been involved on different projects on structural monitoring funded by different agencies. For instance, the project on the left, ROE Tool, this is a European project with focus on interoperability. This one, DS2 and Make4 Pro, are two projects funded by the national government, and specifically by the INAIL agency, which is the agency for protection of workers. And the focus was on sensing and edge computing. And the last project is funded by a private company that is one of the owner of the railway infrastructure. And here the focus was on real-time analytics. So in some of these activities, we were asked to work on the generation of a digital twin of a civil structure, where the digital twin should be able to get real data in real time, of course, to process the data coming from the sensors installed on the bridge, to run anomaly detection, and to classify the type of damage. So at the very beginning, when we start working on this field, at least my initial impression was, okay, this is mainly an implementation task, and the architecture is pretty straightforward. So we have some sensor installed on the bridge. We get the data. We store the data in a database. We run some machine learning algorithms, and then we get the alarm. Was it really that simple? I would say no, because we had to face several technological and scientific challenges. For instance, challenge related to big data management, because in one project, one founded by RFI, every single bridge was able to produce more than between 5 and 10 gigabytes per day. And so, of course, we need proper data management solution, because in order to cope with the scalability of our system. Then there is the problem of the processing. So where to run the processing? We cannot run the processing on the cloud, because probably we are going to transfer too much data from the field. We cannot process the data on the edge, because we don't have enough computational resources. So we had to come out with solutions able to allocate workload dynamically over the edge cloud continuum. Another big challenge was the training, because we want to use machine learning. We had to use machine learning solutions to classify the type of damage. However, when we collect data from the bridge, we only collect data referred to one specific structural state. And we cannot pretend to damage the bridge just to collect labeled data referred to one damage. And the third challenge was the challenge of interoperability, because in a practical scenario, specifically referred to bridge, there might be many different sensors installed over the structure, belonging to different types, and with different protocols and different data formats. So, for instance, in a typical structural monitoring setup, we might use accelerometer, gyroscope, strain gauge, acoustic sensor, inclinometer, displacement sensors, temperature sensors, and in some cases they are provided by different companies, and the entity will take care of the processing of the sensing data might be a different entity of the one providing the sensor networks. So in a very preliminary stage of our research, we developed some pilots. In our pilots, we associate to every single sensor installed on a civil structure. We provide every sensor with a Web of Things description, and in a simplified data model, where the property refers to the values we collect from the sensor, the action refers to the commands we can send to the sensors in order to change the configuration, and the events refer to anomaly events we want to track. This was on the initial stage of our research. Then, after some months, we come out with a more, I would say, generic architecture for structural monitoring, rooted on the utilization of the Web of Things in order to cope with the problem of fragmentation of sensors and data sources. So in our architecture, there are 4 different layers: the sensing layer, interoperability layer, data management layer, and sensing layer. And in the interoperability layer is the logical layer, where we try to abstract from the physical characteristics of the sensing system. And in our proposal, we were considering a possibility to deploy 3 classes of WebThing. Sensor-related WebThing, so WebThing associated to each individual sensor, exposing the data produced by sensor as reading properties and supporting actions for the configuration change. Then we have other WebThing associated to every single sensor network, and in that case, the Web of Things includes all the individual sensor WebThing referred to that network, and then processing related WebThing. In this case, the WebThing, they are not associated to a physical device, but they are associated with software tasks that can take data from multiple sensor-related web thing and transform the raw data into higher layer information like features. Like for instance, in structural monitoring, the civil engineers rely a lot on operational mode analysis. So they extract the raw data, they combine the raw data from multiple accelerometer, and they process the raw data of the accelerometer in order to extract the vibrating frequency of the structure as a whole. This can be an example of processing related Web of Things. And for the data management layer, we create a new a platform, a data platform for the structural monitoring. This is called Modron. And Modron is a customization for structural monitoring of another platform developed by Lorenzo Gigli, who is here in this in this chat. So the WoT Store is a platform, and very few words. Sorry, Lolo, for my bad definition. Is a platform supporting the rendering of thing description inside a web application. So basically, through a web dashboard, we can interact with the properties of a web thing. We can send commands, and we can monitor the triggered events. This abstracting from the physical content of the thing. So only based on the processing of the web thing, of the thing descriptor. And Modron is a customization of this generic platform for structural monitoring. So through the Modron platform, we can, for instance, discover the available sensors. We can browse over the list of sensors, check the current readable and writable properties, change the configuration of one specific sensors, or browse the data, visualize the data produced by every single sensor. These are two examples of the deployment of our architecture for two different use cases. One referred to the monitoring of a concrete structure. The other case referred to the monitoring of an hydraulic circuit, and probably more than this picture probably is I think the videos are more effective, and I have two videos with me. The videos refer to some tests we did in a research lab located close to Rome. So in Rome, they have this unique and very expensive equipment called vibrating table, which is on the basement actually. And the vibrating table is able to, let's say, to reproduce the waveform of a seismic event. So on top of the vibrating table here, there is a concrete structure that we built exactly for this test. And there are some sensors, probably you cannot see from but here is one sensor, here is another sensor. There are some sensors monitoring the behavior of the structure, and in real time, we were able to collect the data from the web thing associated to that sensors and monitor the waveform. Okay, now the structure is for now the structure is in quiet condition. Here we are simulating, they are emulating the effect of an earthquake, of a real earthquake that happened in Italy, in Umbria, more or less 10 years ago. So you will see now the structure vibrating a lot, and the purpose of this test was mainly to from one side to assess the reliability of the sensing system, because also the sensors have been developed by our colleagues in Unibo, and on the other side, assess the performance and the reliability of the data acquisition based on the Web of Things standard. And this was also the last slide of my part, refer to the applied science. And now we can move to the second part of the talk, where we discuss how we can support the generation of the digital twin by using the Web of Things. Luca, the floor is yours.
Okay, how Marco previously introduced, this part is more related on the scientific research we did in the last years, more precisely since 2022, about the generation of digital twin, automatic generation of digital twin starting from real data. So we have, we did a first attempt called WoT Wins, where the idea was basically to follow the pipeline that is depicted here. So we have an environment that is an IoT environment mapped through Web of Things. And the idea is that we can try to guess how the model for our digital twin is made, observing the interaction among the entities of the environment, so among the IoT devices. Once we obtained a digital twin, we can then interact with these twins in order to have, for instance, what if analysis. So basically, we have the real system that we mapped in this particular case. We can think about using some system API. Then we monitor the states, how the states of the environment evolved during the life of the environment. We basically build the transition among the states, and for this particular work we use MDP, so Markov decision process, and then thanks to this we can spawn the twin with the same API, and we can interact with it basically in the same way. So how is the digital twin modeled? Basically, as I said, through a Markov decision process. We have some states, we have some actions. The states are basically, we can say, the parameters, the variables of our physical devices. The actions are exactly those actions that can make the device move from one state to another. And I will be more precise in the next slides. Then we have some transition probabilities that are exactly computed, counting the occurrences that happened for a specific transition. And then we can have some reward function, for instance, in order to enable some kind of reinforcement learning if we have, for instance, to achieve a specific goal. So more in the details, the states in our case were some configurations of property values. So the combination of some properties of the thing description. In this, let's call investigative work, we use some discrete and finite values for our properties. Of course, this is a simplification, but it was a preliminary work. And the actions were basically some actions that performed some kind of variation of the properties. So, for instance, in this example, we have the simple counter thing description that is online, that you made online for us, and we have the counter that is an integer, and we have a random action that basically can move the counter from one value to another, in particular from 0 to 2. So the states of the of our thing basically are 0, 1, and 2. And if we perform the random action, we can move from one state to another. Now, this is a very simple example for the for the sake of ease. Of course, we use this for having a very small, complete diagram. As you can see, by observing, by taking the values from the interactions that happened in the thing, we can basically reconstruct the MDP. So we can reconstruct the probabilities of moving from one state to another, simply counting the occurrences in a specific interval of time. So basically, we compared three different approaches. One is frequency-based, as I explained. The probability T is estimated from the occurrences that happened for the transition. Then we have a machine learning approach using in particular artificial neural network that basically was trained on the observed transition. Then we have an hybrid approach that is used that basically uses both the frequency and the machine learning approaches. The first only if we have a good number of samples for constructing the MDP graph. Otherwise, it uses the machine learning approaches. We evaluated this proposal by using a ground rover simulator, in particular through a grid scenario that was perfect for our discrete case, in which our properties must be discrete values. We had one property for the X coordinate, one property for the Y coordinate, and an action that simply moved the ground rover through the grid, so moving from one cell to another. Here there are some experiments. Of course, we invite you to read the paper if you are interested in more details. But the idea is that we compared on the left the impact of the grid size for our frequency-based approach, and of course the bigger is the grid, and the less precise, less accuracy we obtain from the frequency-based approach, while on the right we have the impact of the type of estimator. So basically we compared our three approaches, and we see that the hybrid approach is performing quite well compared to the others, because of course it can balance the two others approaches. Then we moved to a more sophisticated approach. This was quite long work. It's called relativistic digital twin, bringing the IoT to the future. Why relativistic digital twin? We got inspired by the twin paradox, in which basically two twins could have different age. If one of these twin start traveling in the space. So our idea was to have the possibility to automatically launch the twins and possibly to interact with them at different times of their life. In this sense, the same twin that basically was creating simultaneously with another one could behave in a very different way, okay? Because simply it is older. The pipeline is more or less the same of the previous work, but in this case, we worked a lot of the idea that the thing description could have a domain knowledge, could have the possibility to describe the behavior of the property. So we have the behavioral model inside the thing description. This approach is definitely application agnostic. It means that if we know how to model the mathematically model the environment, we can describe basically every kind of application, every kind of scenario. And the interesting part is that we are able, for each kind of scenario, to launch the digital twins to interact with them as they were physical devices. So with the same kind of affordances. So we started from an IoT system that is heterogeneous. We can have devices that have only sensing capabilities, that have only actuation capabilities, or that can have both of them. Then we map the scenario into thing description, and for each device of the scenario, we add some model information. And for the model information, we enhanced a bit the thing description. So we are here also today for making some kind of proposal to the working group. Of course, this is a scientific proposal, but it is something that will be really interesting, especially, I would say, for industrial scenario where you know quite well the models of the machineries. After the mapping phase, we basically have the possibility to train the models basing, of course, on real data, and then we can spawn the digital twins and we can interact with them, as I said, in a normal way as they were the normal things. The architecture, I would say, is not quite complex. We have the possibility to collect data for the training both from a simulator, like the first paper I presented, or from physical devices. And then we have the possibility to train the models according to different techniques. So we used optimization techniques in this work, but we could easily use also machine learning or deep learning techniques, simply writing the code of these approaches. It's just a replacement of the code in the system. Very briefly, the digital model formalization in this case was made splitting the variables into read-only and writable variables. So each readable property is associated with a set of functions that could be algebraic equations. That means that we can have an instantaneous value of a specific property, or we can have a differential equations that in that case must consider also the time. So in order to get a value, we have to basically integrate over the time a physical quantity. Of course, the parameter of these equations must be estimated from the data and then from our learning module. Another assumption, very important assumption, is that we assume to have some knowledge about the models, but we can assume to have the knowledge because our idea was to propose this kind of framework in scenarios in which there are engineers that perfectly know the model. In other cases, like the evaluation we perform for this work, we used some very well-known physics laws. Okay, like for instance, for the temperature of the room we used in the evaluation. We extended the thing description syntax, in particular with the 3 terms. The namespace here is just a proposal, and of course it doesn't exist, but it could be definitely implemented. We have the model. The model is, as the word suggests, the mathematical model of the property inside the property affordance, and it is simply a string. Then we have a model input that contains the inputs of the model, because a model could depend on other properties of the thing. if we think about a scenario in which we have to model the temperature, of course, depends, for instance, on the heater, and for instance, on the cooler, on the window open, and so on. And then we have the value from, that is a term that simply indicates whether we can have, we can take the value from the read property, or we have to compute it, because that property, it refers to, contains a model as well. We, of course, had also to propose a syntax. We got inspired by Python, so it is a Python-like syntax. We have the behavior that, as I said, could be an algebraic expression or a differential equation, depending on the fact that is a fixed value that does not depend over the time, or the contrary, a differential equation, so it depends over the time. Then we have the function that is an arithmetical expression, and for this we had to, of course, add a few keywords, let's say, compared to the Python set of words. And then we have some constraints that are the preconditions regarding the parameters of the model, and then some guess that can be provided as initial value for helping the tuning of the model, the optimization of the model. So if we have an idea about which kind of values could be found by the model, we can start from those values. The model input is a list of other properties that the web thing uses within the model. So we have a title that is a friendly name. We have the property name that is the exact name of the property of the web thing that such input is referring to. Then we have the type. It is a JSON LD type. We have a model that is exactly following the same syntax described in the previous slide, and the model type, that is an optional field denoting a class assigned to this input. This is useful whenever we have a property model that uses a class of models. So instead of using just one single model, it uses all the models belonging to a certain class. So for instance, the temperature will use all the models that, of course, affect the temperature. So we use an input time of the type temperature. The value form, finally, is a term for describing, as I said, if a value could be provided from the read property, so directly from the sensor, or instead from a model, and in that case, it must be computed. This is a very quick example. We have a model for the cooler. We have a physics law that was coded in the model term that depends on the cooler set point, so the value of the cooler. The cooler set point is described in the model input, and it is, for instance, a value between 0 and 9. And then we have the guess and the constraints value in the model. This is the dashboard, the implementation part. I don't know if you can appreciate, because it is quite small, but the idea is that very comfortably from a dashboard you can train, you can spawn, you can make the what if analysis. So here, for instance, you can see some plots that show how the models, the digital twin, perform over the real data. In the last screenshot here, you have some what if analysis. So here at the bottom, you have the graph showing the values obtained whenever you performed some actions that you invoked from the dashboard. I'm almost at the end of the presentation. Just to tell you that we performed a lot of evaluations for this work. In particular, this was for a quadcopter that we mapped with some write-only properties, the throttle, rudder, elevator, aileron. Then we measured some read-only properties that were used to basically train the model. The models were a second-order linear dynamics, quite famous models for quadcopters, and we learned the data. We learned the parameters from the data in order to obtain the digital twin. We performed some evaluations, and of course, the more we observe the real data, so the more data we collect, and more precise will be our model. I think that, yes, after 15 seconds of observation, we start to reach pretty good results if you follow the lines here, the red and the green ones. For the future, we are focusing on other IoT domains, in particular healthcare, for 2 national projects. We are integrating behavioral model learning and MDP parameters through deep learning techniques. And then we are extending the relativistic WoT framework for federated digital twin environments. So instead of having a single environment containing multiple devices that could be represented as a single entity, one description per each entity, we start to work on this generalization in which we have very different entities, and we try to arrange the relativistic WoT framework for performing exactly the same thing. Well, thank you, and we are open to your questions.